Okay, so let's talk about convergence results now. Again, this is all without proofs. The book doesn't have convergence, proofs of convergence of these methods, but we will still merely write them down so that we can remember them without proving any of these. So first result is that if our given function f is convex, then BFGS converges superlinearly. Okay, so not only it converges to the minimum, local minimum, but also much faster than linear convergence. Okay, if G of x star is positive definite. So we would like the Hessian at x star, the optimal point where we want to converge, to be positive definite. Note that since f is convex, then the Hessian will always be positive semi-definite. This result holds even for inexact line search. We can't extend this result to DFP or other members of the Broyden family directly, because here we are doing inexact line search. So I will write this down, that the above result number 1 is not easily extensible to the rest of the Broyden family, even though some researchers have later shown that even with inexact line search, everything in Broyden family can converge to a local minimum. What about the case when the functions are not convex? So we have not really discussed formal definition of a convex function. I hope most of you are familiar with it. A convex function is a function which has a shape like this. Its Hessian is positive semi-definite everywhere, and if I draw a line joining any 2 points on this curve, the curve will lie below that straight line. So that's the definition of a convex function. These functions are nice in the sense that a local solution is also a global solution. We'll come to convexity a bit later, but for now we just want to look at what happens when my function is not nice. So convex functions are nice because they have a nice local minimum, which is also the global minimum. But in case of non-convex functions, there have been some recent results which show that these methods may actually fail. So BFGS may fail, or actually there's an example fails. when we do Wolf's condition in line search. That doesn't mean that DFP and everything else should also fail, because we are talking about inexact line search. And this result has been presented in 2002 by Dye. So if you are interested, you can download this paper by Dye in 2002, which tells us, constructs a complicated example to show that it may fail to converge. Then later, to 2004, some researcher called Mascarenas and they showed that even exact line search is not enough. That BFGS with exact line search fails. And this is a strong result, because once we are doing exact line search, then it means that I can replace BFGS by the whole Broyden family. So that means DFP also fails sometimes for non-convex functions with exact line search. Okay, so these are fairly negative results in my opinion. But what this work also shows is that there has been recent work on this method, even though this method is very, very old, starting from 1960s and 1970s. It is quite popular and of interest to many people. So we keep seeing newer and newer results as time progresses. So 30 years after the method was proposed, we were able to show, or at least somebody was able to show that the method may sometimes fail. Okay, but practically, so this is a theoretical result. And the function, by the way, is not that straightforward. It is quite complicated, and it requires reading these papers a little bit carefully to understand and what that examples are. But what this result means is that the whole Broyden family fails with exact line search. That doesn't mean that we should not use it, because practically very useful. Especially BFGS. It is one of the gold standard in algorithms for unconstrained nonlinear optimization, and it has been used by many solvers and packages to solve general purpose problems. So this BFGS has had a huge impact on unconstrained optimization, and it is still popular for many of the optimization problems which have many variables like in statistics or machine learning. There's a huge number of results, large number of results theoretical as well as algorithmic or computational, and it's a bit difficult to actually keep track of everything that is happening in this area, but extremely useful in practice and should be used if they don't run into any trouble. These methods have many variants. So one variant is LBFGS. This is also very popular. In LBFGS, we avoid storing HK plus 1, etc. Okay, because they might become quite dense actually, these matrices, and remember that these are square matrices of size n cross n. So if I have n equal to 1000, then I already have 1 million values to take care of. It also avoids complicated multiplications of some of these vectors and matrices by reusing what we calculated earlier, and this is especially useful for very large scale problems. Okay, so very large scale problems. Okay. We don't have time to go through these methods. LBFGS is, I don't think it is explained in the book, but overall these methods are very exciting in the sense that they are fast and practically very useful, but at the same time very challenging theoretically. As of now, we don't know whether these methods will always work, regardless of whether we are doing exact line search or approximate. So this area is quite vast, and if some of you want to explore this more, I can try to provide some references to you. So we will end this chapter, discussion on this chapter of Quasi-Newton methods here, with the conclusion that these methods can be very fast and very effective, but at the same time technically there is a small chance that they might actually fail to converge. So summary is steepest descent is globally converging is somewhat slow, Newton's method may not converge. And every iteration is expensive. Quasi-Newton methods, like we have discussed, rarely don't converge. Rarely fail to converge. And out of these three are typically the fastest. So it's great to use them, and also it's nice to do further research on them. And there are people who are still working on these methods, even though they are now more than 30 years old. So with that remark, I will stop and hope to see you in the next lecture.